What about the feet?
So massive. Again, not surprisingly, you're supporting a colossal amount of weight, but they have this beautiful adaptation in the foot. So the equivalent bones in the foot, the metatarsals, so for us make up the flat of the feet, but these animals walk like birds. They've got 3 toes on the ground, and then the metatarsals stick nearly vertically. Now, it overall extends the length of the leg, so you can walk a little bit faster. You get a slightly bigger stride length. Don't worry, I've got the right bone here.
Nice.
But they also have, yeah, there's a good one. That one's a great one. But they also have this really neat adaptation in the middle bone. So you can see it on this one quite well. And that this is actually not a tyrannosaur. This is an ornithomimosaur. So one of the really ostrich-like ones, Gallimimus from the first Jurassic Park. It has the same thing. You can see the normal bones would be really quite long and square and then flat at the top. And instead, this thing shrinks in the middle and turns into this kind of flattened diamond shape. And what that means is the bones either side kind of lock it. In fact, at the top end, it actually tends to wiggle a bit. So it actually goes left and then right. And of course, what that really does is then help these things lock together. And so this is an adaptation to basically lock the foot and make it stable. And we see it in a whole bunch of things, independently evolved. Early tyrannosaurs don't have this. Early ornithomimosaurs don't have this. The oviraptorosaurs, the early ones, don't have this. And the later ones acquire it. And a couple of other groups as well. And it's about making the foot stable. And what that really does is make the foot energy efficient. So you can imagine, as an animal, you know, we have some cartilage and we've got some ligaments and tendons joining all the bones together and holding joints stable. When you push down, that's going to compress them to a little degree. And when you lift that weight off, they're actually going to spring back. You're going to get a tiny little energy return. It's the idea of those air soles they put in all the trainers and stuff in the 90s. It's that same principle. And you'll get a little bit of energy return. But of course, big force, particularly for a big heavy animal, it's going to take the kind of path of least resistance. And so if your bones are all kind of loose in the foot, what they're going to do is they're going to tend to splay out, and you're actually going to lose that energy. But if you lock the feet together, the bones can't move, and instead that's going to further compress those soft tissue bits and give you a bit more spring.
And this is all about, this is about the mobility, about the dynamics of the movement.
It makes you more efficient. It means you're putting less energy in to walk because you're just getting a little bit of spring off every single step.
I should say that I deeply admire people like Russ Tedrick, like the Boston Dynamics teams, like the Tesla Optimus robot teams that look at bipedal and quadrupeds robot movement.
Yeah.
And they try to make human-like movement to, basically efficient movement. And so the question here is, how the hell is a T-Rex, its size, bipedal, able to move as a predator? It's a weird body shape, is it not?
The big head makes it look more odd, but you look at dinosaurs as a whole, and over a third, probably 45% is the group called theropods, which were all bipeds. So T-Rex, Allosaurus, Velociraptor, Spinosaurus, many, many others that people may have heard of. They're all bipeds built in this way. There's a whole bunch of ancestral groups which were doing something very similar, including various crocodiles or relatives of crocodiles. And then the birds are bipeds. Birds are actually doing it in a much weirder way than theropods are. The theropods are basically a lizard on its back legs. I'm oversimplifying a lot. I can hear paleontologists screaming as I've just said it's a lizard standing up. It's not a lizard standing up. But they're doing a lot of the same stuff in the same way. And that is really functionally about where you put muscles. Because what you really want to do to walk forwards is you want to basically pull the leg back so that you're pushing the body off. Mm-hmm. And the way they do that is the musculature on the tail. So we don't have a tail, and indeed mammals that even do have a tail, elephants and even lions, it's a piddly little thing. There's not a lot of muscle there. But if you look at a lizard, particularly if you look at something like a crocodile, you see this massive, massive block of muscle sitting on the first third to half of the tail. And that's what dinosaurs are doing. It's the same thing as lizards and crocs. They have this giant set of muscles on the first half of the tail that's anchoring on the femur, so the thigh bone on the back of that, and muscles contract. That's the one thing they do. But now you've got a giant muscle. Yeah, and T-Rex, this muscle's like 2.5, 3 meters long. Mm-hmm. It's going to be like this wide in the middle. So when that contracts, the leg goes back, foot stationary on the ground, so the animal goes forwards.
So the tail is
integral to movement.
It's a huge part of the biomechanics of the movement.
We do it with the butt. So we're kind of weirdly how we organize our muscles. But this is generally probably a better way of doing it because you can get a really long muscle. And of course, the longer the muscle, the more contraction you can have. The hyper version of this is kangaroos. So kangaroos supposedly get more efficient the faster they move. They get so much energy return that when they're moving faster, they get more compression from the landing, meaning they get more spring.
So we should be imagining this gigantic, thick tail, big body, big head.
Yep.
And biped. And how fast does it move?
So this is one of those things that's gone backwards and forwards and backwards and forwards. There was a paper arguing that we'd probably been overestimating various speeds, primarily based on footprints. There's been, I don't know how many papers trying to do T-Rex speed. The most recent one that was pretty detailed, I think had it clocked at, so I think it was 25 miles an hour, so 40 kph was the very upper end of the estimate. So probably a bit less than that.